Welcome to your Chemistry of Life presentation. Here are your objectives for this unit. And I started off with something that hopefully you've all seen before. This is the periodic table of elements. This table consists of all of the elements that are currently known to man. Every square on here represents a naturally occurring pure substance, which is an element. Each element has an abbreviation of 1 or 2 letters. For example, carbon is C, hydrogen is H, chlorine is Cl. And you'll see that in the upper left-hand corner of each square, there is a number. That is the atomic number. And that is going to be an important number for us to remember as we move forward. The good news is that I'm not going to be asking you to memorize numbers from the periodic table. And we're really only going to be looking at a handful of elements in our study. I also included for you here a link at the top, so if you want to download your own copy of the periodic table to keep with you, you can do that. So to start it off here, we're going to have a discussion about atoms. Atoms are the building block of all matter. That includes living and non-living things. So everything on the earth is composed of atoms. The difference between an atom and an element is that all atoms of a specific element, for example, gold, which you see in the picture, gold is an element, all the atoms of gold will be identical and they will have the same properties. So if you were to say that something was pure gold, you would know that it is composed of 100% gold atoms and nothing else. So we do find pure substances like that, but also we have atoms of different elements that join together to form molecules and compounds. We need to take a look at the basic atomic structure. And that includes looking at the 3 subatomic particles: the proton, the neutron, and the electron. If you look on the top picture here, you can see that both the proton and the neutron are located in the center, and the electron is at the periphery or the edge. So in the center of an atom is found all of the protons and neutrons. They are very densely packed inside a structure that we call the nucleus. Nucleus always refers to the core or the center, while the electrons are found outside of the nucleus. And you notice that 2 of these 3 particles actually have an electrical charge. The proton has a positive charge, the electron has a negative charge, and the neutron is neutral, so it has a 0 charge. Here's a look at another atom, a little bit larger atom. You can see that all the protons and neutrons there very densely packed in the center. And now you can see that when we build larger atoms with more protons and electrons, this atom, you can see, has electrons that are arranged in 2 distinct layers. And we call those layers orbitals. So you can think of an atom like the solar system. In the solar system, the sun is at the center and is stationary, while the planets actually orbit the sun. And the same is actually true of electrons. Electrons are not stationary. We are drawing them as if they are, just for simplicity's sake. But the reality is that electrons are actually moving in space. They're moving in 3 dimensions, much like a planet would orbit the sun. So in this atom, if you count the electrons, there are a total of 10 electrons. They are arranged such that there are 2 electrons in the inner shell and 8 electrons in the outer shell. And those numbers actually represent the maximum number of electrons that those shells can hold. So 2 for the inner and 8 for the outer. One more thing to point out. If I were to ask you to identify this atom, what element is it? Well, you can't necessarily count all of the protons or the neutrons that are in the center, but what you can count are the electrons. It's also very important to know that an atom, by definition, has an overall 0 charge. It has a net neutral charge. So you know that if you have 10 electrons, you also are going to have 10 protons. So then, if you wanted to find out what element this is, you would look on the periodic table, find the element with the number 10, and you would find that that element would be neon. The last thing to note on this slide is that when you build atoms, you have to fill the inner electron shells first. So you would always put 2 in the inner shell before you would move on to the outer shell. It has to be full of 8 before you could move on to the next shell. This is a picture of the periodic table, a portion of it, and it actually has the atoms with the electrons drawn in. So every atom has a nucleus at the center, and then it has the orbitals surrounding. So you'll notice that if you look at the atomic number, so the atomic number on this periodic table, the atomic number is going to be this number in the upper right hand corner. So for hydrogen, the atomic number is 1, helium 2, so on and so forth. And so really what the atomic number actually does is it actually corresponds to the number of protons. So the number of protons actually defines the element. Okay, so here is our atomic number. Okay. Here's our atomic number, 1. And there's 1 electron, also 1 proton. So let's say then if I come down here to say argon, atomic number 18. So there would be 18 protons in the nucleus, but the protons aren't shown in here. And then you count the electrons, you'd have 18. Another important word on this slide I need to identify for you is this word valence. Valence refers to the outermost shell, outermost electron shell of an atom. And when it comes to chemistry and understanding how atoms behave, the valence shell is the most important. Also, understand one more concept is that atoms always want to fill their valence shells. So, for example, if I'm carbon, sitting right here, if I were to ask you to identify the number of valence electrons in a carbon atom, you would tell me 4. Now, my next question, is this a stable atom? In other words, does it have a full valence shell? The answer is no. So that actually is a very good thing in terms of biology, because that's going to make atoms like carbon highly reactive. It's going to help us actually to build larger molecules within the body. All right, let's erase these here. And we are going to draw an atom. So what I'm going to do for you is I'm going to draw for you the shell of an atom. And I'm going to ask for you to fill it in. So let's say we're going to draw our nucleus here. And how many protons do we want to put? Let's just say, let's say 8. I'm going to put 8 protons in my nucleus. Okay? So the next thing that I want to do is put my electrons in. So to do that, I need Okay, so we are going to draw an atom here. So I'm going to draw for you. We're going to put a nucleus here. Oh, let's get a different color. We're going to draw a nucleus here, and I'm going to put in that nucleus 8 protons. And there also would be 8 neutrons in there, but I don't really care about the neutrons, okay? The next thing that I need to do is put my electrons in. So I have to put my orbital And so remember, this innermost shell is only capable of having 2 electrons. So clearly that's not enough. So I have to then put another orbital. Let's see if I can make that a little bit better here. That'll work. So I'm putting my second orbital, and so I have 8 minus 2. I have 6 electrons left to go. So that would look something like 1, 2, 3, 4, 5, 6. Now, the way I'm drawing the electrons like this is really arbitrary because remember, these electrons are not stationary. They're moving in space. The most important thing is that you have the correct amount of electrons in the orbitals. So I've completed my drawing. The last step that I need to do is identify what atom this would be. So you go to the periodic table, find the atomic number, and you would see that this is a carbon atom. So I most definitely would encourage you to practice drawing some atoms on your own. The ones that are going to be the most important for us, I'll make you a short list here. Carbon is very much important for us. Hydrogen, oxygen, nitrogen. Other atoms we're going to look at, sodium and chlorine. Also, later on in the course, we're going to look at sulfur, which is S, and phosphorus, which is P. Those are really the main ones for us. All right, so here is what actually an atom would really look like in 3 dimensions. Okay, the electrons are moving in space and orbiting the nucleus, creating what actually we call an electron cloud. Okay, as opposed to the concept of a shell. It really is actually a crowd. Excuse me, a cloud. So looking at these atoms here, I want you to make the correlation between the number of valence electrons and the reactivity of an atom. So if you notice on the left-hand side, hydrogen has 1 electron in its valence shell, carbon has 4, sodium has 1. What do all these 3 atoms have in common? They have a valence shell that is not full. So what does that mean? That means that these atoms are unstable, highly reactive. On the right-hand side, I have a helium that has 2 valence electrons, neon with 8, argon with 8. So these numbers right here actually represent the maximum number of electrons that these first 3 shells can hold, 2, 8, 8. Okay, so these are full valence shells, stable, very much unreactive atoms. So here's a checkpoint question for you to make sure how you're doing with the lecture. Which subatomic particle is involved in the formation of chemical bonds? So subatomic particles, there are three choices. Your choices are the proton, the neutron, or the electron. And I'm not going to tell you the answer. All right. Another question for us. Sulfur has an atomic number of 16. I want you to practice drawing sulfur and tell me how many electrons are in its valence shell. All right, now that we've discussed the basic structure of atoms, we can look at how do atoms interact with each other to form chemical bonds. And as you hopefully guessed in one of the previous questions, atoms form chemical bonds by virtue of electrons. And they have a couple different choices when doing so. When two atoms meet or come together, they can either decide to have a transfer of electrons, whereby one atom would actually give up or donate an electron, and the other atom would accept or take it. So that example is actually being shown right here. You can see one atom is actually giving an electron to the other. Okay, this creates for us the formation of ions. Okay, ions are atoms that have a charge. So it's either going to be a positive or a negative charge. The other option that atoms have when they come together is that they can decide to actually share their electrons to satisfy their valence shells. On the right-hand side, here's an example of two atoms that are sharing a pair of electrons to become more stable, and this creates what we know as molecules. All right, I'm going to give for you an example of two atoms, and I would like for us to predict how these two atoms might interact. So let's draw a nucleus here, and we'll go simple. We'll just have one proton in our nucleus. Therefore, I know that I need to have one electron. And this atom on the periodic table, you look it up, you would find it's hydrogen. Then I'm going to draw a second hydrogen right next to it. So here these atoms are. They're face to face. And is either one of these atoms stable? The answer is no. Their valence shells are not full. So here are the options. One hydrogen could actually donate its electron to the other. So that would look something like this. But then think about what that would do. If one hydrogen donated it, then one would have two and the other would have zero. So only one of the two actually would be stable. So that's not quite what we want. So what's my other option? My other option would actually be to have these two atoms share the electrons. They would share their pair of electrons, and therefore this pair of electrons technically belongs to both atoms at the same time. This creates for us a molecule of hydrogen, H2. Okay, let's clear this. Okay, I'm actually going to go back. And we're actually going to look at another scenario of electrons, different atoms this time. Okay, so I'm going to draw over here, I'm going to draw an atom with 11 protons. Fill in my electrons. 2, 8 gives me a total of 10. So I actually have to go to the third shell to get my 11. Okay, atomic number 11, this is sodium. The other atom I'm going to draw has 17 protons. Fill in the electrons. Okay, there's a total of 10. Third shell. Okay, so I have 2 plus 8 plus 7. That gets me 17. Okay, this is atomic number 17. This is chlorine. So let's look at the valence shells. Okay, sodium has a single valence electron. So what might it do? Well, it could either try to find 7 electrons to fill its shell. So it would have to find 7 other atoms that are willing to give up electrons. Or it could actually donate this electron. It could get rid of it, but it has to have somebody to give it to. And in this case, we have the perfect recipient here. That would be the chlorine atom, because chlorine has 7 valence electrons, only looking for 1 more. So what happens in this case is sodium will donate its electron, its valence electron, to chlorine. Thereby giving chlorine an extra and sodium has 1 less. So when you get rid of this electron, then you also get rid of that third shell. So that makes the second shell the outer one, and that indeed is full. But now we have a situation where I actually have uneven numbers of protons and electrons. Notice I didn't do anything with the proton numbers. I still have 11 protons for sodium. I got rid of 1 electron, so I have 10. That gives me a net charge of +1. So this is an ion. This is a positively charged ion. What about chlorine? Chlorine started off with 17 protons, and it gained an electron. So that leaves me with a net charge of -1. So chlorine becomes then a negative ion. Have you ever heard the saying, opposites attract? That's exactly what happens here. Sodium and chlorine are attracted to each other in an ionic bond. So here's what that looks like from another view. You can see sodium donating that electron to chlorine. See the formation of the ions and the attraction of the opposite charges. You might be more familiar. This compound is sodium chloride. This is known as, this is table salt, sodium chloride. Okay, a little bit of terminology here. When you have an ion that has a positive charge on it, we call that specifically a cation. Okay, so cations are atoms that have lost or donated electrons. Okay, and these always have to go together. Okay, you can't have an atom that just gets rid of an electron. It has to have somewhere to go. So an anion then is an electron acceptor. So it's gaining an electron, but remember, electrons are negatively charged. So it's kind of like the same concept as subtracting, excuse me, wrong train of thought. It's but an anion has a negative charge. There's also an animation here that's linked. You can click on this animation to see a little clip about ionic bonds. Okay, this takes us back to the very first example that we looked at. The very first example actually that I drew for you was this top example right here of having two hydrogen atoms that share their pair of electrons. So when when atoms share electrons, this is called a covalent bond. I really like this word. I think it does a very good job of describing what's happening. Okay, co means with or together, and valent as in the valence shell. So what you have are two atoms that share electrons together so they both can reach their valence shell. Other examples that you see here, oxygen. When you put two oxygen atoms together, they actually can share two pair of electrons. They can share a total of 4 electrons. So you see this symbol right here between the two oxygen atoms, it looks like an equal sign. That actually represents a double bond, whereas single line for a single bond. Okay, carbon dioxide, also a molecule, uses covalent bonding. I'm not going to play this clip right now, but this is actually a video clip that will illustrate for you covalent bonding. So you can go ahead and pause the recording and watch the audio clip. Okay, we need to spend a little more time talking about covalent bonds. I know that some of you have children. And so what if I asked you a question? If you gave your children a bunch of toys to share together, could you guarantee that they would share those toys equally between them? And I'm guessing the answer is probably no. So atoms behave actually much in the same way. Atoms do not always share electrons equally. So if you look at the pictures here on the right-hand side, one pair of atoms is sharing equally and the other pair is not. And so how can you tell? Well, the gray shadows that you see behind the atoms represent the electron clouds. And you can see in the top picture that that cloud is nice and symmetrical. So that shows us that these atoms are indeed sharing electrons equally. But the bottom picture, however, not so much. That is not an equal distribution, so there is unequal sharing here. So we know that this is equal sharing, this is unequal sharing. So why is that? Well, just like children, just like people, certain atoms, I like to call them electron hogs. They just really don't like to share electrons. Okay, there's actually a term for that. The term is electronegativity. It means it's a measure of how much an atom likes electrons. So for the atoms that we're going to discuss, oxygen is the atom that actually likes electrons the most, more than anyone else. So that's why when you look at this electron cloud here, it's very much a larger cloud around the oxygen than it is for the hydrogen. So what this is indicating is that as these electrons are orbiting both of these atoms, they are spending more of their time closer to the oxygen atom. So now that we've talked about equal and unequal sharing, we have terms for that as well. The top picture, nice and symmetrical and equal sharing. This represents a nonpolar covalent bond. Okay, still covalent because it's sharing. The bottom down here, this is a polar covalent bond, still sharing, just not equally. So if you think of that word polar or just the word pole, think of like the North and the South Pole, for example. What do you know about them? Well, they're on opposite ends of the Earth. Or maybe you've heard the phrase polar opposites. So something that's polar means that it's got two ends that are different. They're not the same. For example, if you were to look at a pencil has one end that's sharp and pointed with lead so that you can write. The other end is soft and squishy with an eraser. Okay, so a pencil, you could say, would be a polar object. All right, so polar and nonpolar covalent bonds. Nonpolar has equal electron sharing, polar has unequal. All right, so here we've got an example here of a polar and a nonpolar molecule. The top molecule that you see has a molecular formula of CH4. This is actually methane. Okay. And on the bottom, we've got good old H2O. So methane, if you look at this methane molecule, you can see that these electrons are very evenly dispersed. So this is indeed a nonpolar molecule. Looking at the water molecule, though, down below, these electrons are very much concentrated around this oxygen nucleus. All right, so this is a polar molecule. Remember, oxygen really likes electrons most of all, so it's hogging them. Another way I like to think of electronegative atoms like oxygen, I like to think of them like electron magnets. Okay, so if you can imagine this oxygen nucleus like a magnet. Okay, and it's pulling all the electrons close to it. All right, so what that actually is going to do then to the overall molecule is it's going to create a charge separation and no longer have a symmetrical distribution of charge. So you notice I have this little symbol up here. It kind of looks like a squiggle or almost like a number 8 with a negative sign next to it. Okay, the symbol actually is a Greek letter. I believe it's gamma. But the fact is that it's negative. And so what that symbol represents is it represents a partial charge. So this is a partial negative charge. And then down here, I have my partial positive charges. Okay, this is actually very significant in the behavior of this molecule. This particular example is water. We have a whole separate unit that we're going to talk about water. But for now, you need to remember that water is polar. It exhibits unequal electron sharing, which results in partial charges within the molecule. All right, next checkpoint. Give an example of a molecule that exhibits polar covalent bonding. Next question, type of chemical bond whereby electrons are transferred from one atom to another. Only one correct answer. So here's kind of a nice snapshot. The 3 types of chemical bonds that we've talked about so far. So I would maybe make a little star on this slide and emphasize it. To come back to it, there's a lot of information on here. You can see the shape of the electron cloud, the symmetry, the partial charges for your polar covalent bonds. So this is just kind of a recap of the last several slides. Okay, so I'm going to draw you a lovely picture here. Okay. Okay, this is a beaker, obviously. It's a beaker. And inside of this beaker, I am going to put a bunch of water molecules. I'll just do 3 for now. Right? So I have this whole beaker full of water molecules. And remember what we just got done talking about with the water? That every water molecule, since it's polar, is going to have these partial charges on it. Always the oxygen carries the partial negative and hydrogen carries the partial positive. So what do you think might happen when you get a whole bunch of water molecules in close proximity and there's a bunch of partial positive and negative charges? Well, as we said earlier, opposites attract. That same thing holds true. Okay, so what I'm actually going to see, I'm going to see, draw a little dotted line here. Okay, and here. Trying to make sure you guys can see that. Okay, so I'm drawing some dotted lines in between these oxygens and the hydrogens because that's exactly what happens. A hydrogen bond is not technically a chemical bond, so to speak. It is actually more of a weak attraction. So maybe this might be like what would happen if you had a crush on someone. Okay. So you have a crush on someone and you walk by them in the hallway and maybe your face turns red or your heart starts beating faster. So there is definitely an attraction there, but there is not a formal relationship between you. Okay, but there is an attraction. Maybe it's one-sided. If you don't say anything, you'll never know. But that's what a hydrogen bond is. It's a weak attraction between partial positive and negative charges. Very important property of water. So here you can see a much better illustration of the hydrogen bonds forming between water molecules. Okay, very last couple slides. I'm going to go through these quickly. Anytime we have chemical reactions, we are actually involving a transfer of energy. You are either releasing energy or you're consuming energy in a chemical reaction. And that energy exists in the form of chemical bonds. Chemical bonds are a source of energy. Okay. Also, oftentimes, chemical reactions will produce heat, also a form of energy. The concept of chemical equilibrium has to do with reactions that are reversible, that can occur both forward and backwards. And when the forward and reverse reactions occur at equal rates, this reaction is said to be at equilibrium. So you can think of chemical equilibrium kind of like homeostasis. When things are balanced and things are equal, then the reactions occur at the same rates. I'm not going to get too much into this slide. In chemistry class, you would do more with balancing equations. But just to illustrate for you a law called the conservation of matter, basically you can't get something from nothing. So when you're doing chemical reactions, you always have to account for all of the atoms. Few questions here to finish up. Hydrogen bonds are stronger than ionic bonds. Is this true or false?